Section 7.5, Solving Initial Value Problems Using Laplace Transforms. So far throughout Chapter 7, we haven't encountered any differential equations, much less initial value problems. And the reason for that is, as we said at the outset, we've been developing machinery involving Laplace transforms and inverse Laplace transforms that would allow us to bring those tools to bear to solve a wide variety of initial value problems. So without further ado, let's try to turn loose everything that we've learned in order to solve an initial value problem. So as an example, let's look at the initial value problem y double prime minus 2y prime plus 5y equals minus 8e to the minus t with the initial conditions y of 0 is 2 and y prime of 0 is 12. Now before we get going in this, let me fully admit that this is a differential equation that we already know how to solve from Chapter 4. If you look at this, this is just a second order, linear, non-homogeneous equation with constant coefficients. We would use, for example, the method of undetermined coefficients to find the general solution here. We could use the method of variation of parameters if we wanted to. We would get a two-parameter family of solutions. We would use the two initial conditions to solve for the constants, and we would be done. So the point of this, I'm not claiming that this is a problem that we never knew how to solve. And matter of fact, I'm starting with a problem that we do know how to solve and just showing you that we can solve that same problem a different way. And we're going to do it with this new way using Laplace transforms, and then we're going to reflect back on what we would have done in the past. And then going forward, we will see more examples of problems that we would not have been able to tackle with the previously learned methods. So here's the workflow. When you have an initial value problem and you want to solve it using the method of Laplace transforms, we're going to start with the differential equation. We're going to take the Laplace transform of both sides of the differential equation. So we'll take the Laplace transform of y double prime minus 2y prime plus 5y. We'll take the Laplace transform of minus 8e to the minus t. By linearity, we can take the Laplace transform of the pieces here, and we can factor out our constants. We can factor out our constants here. And now when we have this, here's where we start to use some of the theorems and machinery that we've developed in earlier parts of Chapter 7. So let's recall that the first derivative theorem said that the Laplace transform of y prime is s times big Y of s minus little y of 0. This would be in our table. And then the second derivative theorem said the Laplace transform of y double prime is s squared times big Y of s minus s times little y of 0 minus little y prime at 0. It's very important that you keep your big Y of s's and your little y's completely separate from one another. And so that means I know what to do with this. This just becomes s squared big Y of s minus s times little y at 0 minus little y prime at 0 minus 2 times, parentheses are very important here, the Laplace transform of y prime is s big Y of s minus little y of 0 plus 5 times the Laplace transform of y. Well, I don't know what y is, so the Laplace transform of little y is just big Y of s. And on the right-hand side, I have my minus 8. And then the Laplace transform of e to the minus t, that's in my basic table. That's 1 over s minus a minus 1, 1 over s plus 1. Now, so that's step 2. For step 3, let's apply the initial conditions, because we notice in this line above that we have an initial condition here, here, and here. So let's apply our initial conditions. Let's simplify. Let's isolate and solve for big Y of s. So here I'm just going to put in, remember our initial conditions were y of 0 is 2. And y prime of 0 is 12. So what we'll do here is wherever I see a y of 0, I'll put a 2. Wherever I see a y prime of 0, I'll put a 12. And then I'll just distribute here with a goal of consolidating everything that has a big Y of s in it. And if I do that, I get this. The right-hand side just is what it is. I will factor out that common factor, big Y of s, from these three terms that are highlighted. And the things that don't have a big Y of s in them, I will export to the right-hand side. And when they're on the right-hand side, I'll get a common denominator and combine these. And then I will solve for big Y of s. So now I have big Y of s. Okay, so what's going on here? Remember what I'm looking for. I'm looking for the solution to this initial value problem, which should be a function little y of t. It should be a function in the t domain. What I have at this point is not the solution to my differential equation. I actually have the Laplace transform of the solution to my differential equation and initial conditions. Notice the initial conditions are already baked into the cake. They were baked into the cake right here. So this is not the solution that I'm seeking. It's actually the Laplace transform of the solution that I'm seeking. So I need to undo this Laplace transform by taking an inverse Laplace transform of both sides here. So let's take inverse Laplace transforms of both sides to get little y of t. So inverse Laplace transform of this is here. Inverse Laplace transform of this is here. I know that the inverse Laplace transform of big Y of s is little y of t. And how would I compute this? Well, we actually computed this in the last section. If you go back and look, this is one of the examples that I used. And so we did a table-friendly partial fraction decomposition on this. I won't recycle all of that work here. You can go back and reference it. But we found this inverse Laplace transform. It came out to be 3e to the t cosine 2t plus 4e to the t sine 2t minus e to the minus t. And we're done. This is the solution to our initial value problem. Okay, so the key idea here is, and maybe we'll reflect on this just a minute. Again, I'm not saying we did not know how to solve this problem some other way. We know that if we were to solve this, say using chapter 4 methods and we used undetermined coefficients, we would take the homogeneous problem, we would find the characteristic equation, we'd get its roots, we'd get our YH, we'd get our YP. We know what the form of our YP looks like. It looks like a constant times e to the minus t. We would put those together so that the general solution looks like YH plus YP. Then we would apply our initial conditions to resolve the two constants that are in there. And you can already kind of see the flavor. If you were to solve the characteristic equation of the homogeneous problem that I just showed, you would get a complex conjugate pair of roots, and this would be your YH, or your YH would have this form, and then this would be the form of your YP, and then these numbers are coming from solving for the initial conditions. So this is reminiscent. We're getting the same type of answer that we would get using our previous methods. We're just doing it with a completely new take using Laplace transforms. So the key idea of Laplace transforms is that they quote-unquote algebraize initial value problems. What I mean by that is if you have a differential equation plus initial conditions, so you have an initial value problem. If you take the Laplace transform of this problem, it maps it to an algebraic equation for big Y of s. If you look up here, once the dust settled, once we took Laplace transforms, right here, once we took Laplace transforms, stare at the aftermath. This is not a differential equation anymore. Stare at this. I know you might see some derivatives, but these are just involving the initial conditions. After we substitute in our initial conditions, look at here. This is not even a differential equation anymore. It's actually an algebra equation in the unknown big Y of s. So this is one of the key features of Laplace transforms, and why we're studying them, is that when you take Laplace transforms of a differential equation, it converts it into an algebraic equation. The trade-off is it's an algebra equation in the S domain. So then you solve in the S domain, but you have to undo the transform. You have to inverse transform to get back to the T domain. So in terms of a diagram, it looks like this. Suppose you have an initial value problem, you hit it with a Laplace transform, you get an algebraic equation in big Y of s, you use algebra to solve for big Y of s, and then you need to recover and get back to the T domain by taking an inverse transform. It's kind of reminiscent in calculus when you do something like a U substitution. You have a hard integral that you don't know how to solve. You make a transformation to turn it into an easier problem that you do know how to solve. You do your solving in the easier domain, but then the trade-off is you have to convert back to the original domain. This is very much like our workflow here in terms of solving initial value problems using Laplace transforms. Let's look at another example. So suppose you had y double prime plus 4y prime minus 5y equals t e to the t. Once again, I fully admit I'm picking a problem that we could solve by other methods. We could do this by variation of parameters or undetermined coefficients. That's not really the point right now. We're going to get to problems that you couldn't do with those methods, but we're just trying to work on all the muscles that we've developed throughout Chapter 7. So if we take the Laplace transform of both sides, we'll use linearity to break this up. We use our theorems to calculate this Laplace transform. This is something we were doing earlier in Chapter 7. So if we look at this as e to the at times an f of t that we know how to transform. Our a is 1. Our function little f that we know how to transform is t. And remember what our shift theorem says? It says that this is going to transform to big F of s minus a, where this is big F is the Laplace transform of my little f. If this is my little f, then this is my big F, and then I need to evaluate this at s minus my a, or s minus 1, and I get this. So the transform of this function in the t domain comes out to be this function in the s domain. I'll use my second derivative theorem here. I'll use my first derivative theorem here. I just leave this alone. And now what we want to do is apply the initial conditions. We had the initial conditions here, so we apply the initial conditions here. And then when we have numbers for those, we gather everything that has a big Y in it together. We get this. And then we have the leftovers that are here that don't have big Y in them. And then the right-hand side is what it is. Then what we do is we take the stuff that on the left-hand side that doesn't have big Y in it, and we export it to the right-hand side. Then we combine these. Usually you have to get a common denominator. You combine these, and then you take the polynomial that's multiplying by your big Y of s. You divide both sides by it, and you get this big complicated expression for big Y of s. But then we know ultimately we need to inverse transform this. And so to inverse transform this, we need to sort of chip away at this and do something like a partial fraction decomposition. So I'll go ahead and take the denominator and we'll factor it. I already see that this part is factored. This is a repeated linear factor. It has a multiplicity of 2. This thankfully factors into s plus 5 and s minus 1. And so we have a repeated linear factor. Well, why don't we consolidate these two into here? So I see that I have a repeated linear factor, s minus 1, with a multiplicity of 3, and I have a distinct linear factor, s plus 5. So I'll go ahead and do the partial fractions. So remember, when we have a repeated linear factor, we count up on our powers of our repeated factor, and everybody gets their own constant in the numerator. And then for this is a different linear factor, so it gets the linear factor in the denominator with its own constant. We have 4 constants here. And I'll just say, after some work, you should know how to do this. We can do the partial fraction decomposition. Really, we're just working on this equaling this. We use the cover-up method. We will find, after some work that I'm not showing here, this is my A, my B, my C, and my D. So that means the inverse Laplace transform of this is the same as the inverse Laplace transform of this. And for right now, I'll just use placeholders A, B, C, and D. It's easier to write than these numbers. And I know what those numbers are, so I can plug them in at the end. And so now I will inverse transform this to get big Y. I'll inverse transform this by pulling the A out, pulling the B out, pulling the C out, pulling the D out. And then if you look at this, I need to make sure everything is doable and table friendly. This is on my table. If you look at this, this is a shifted version of something that's on my table, so I know how to inverse transform this. I have to be careful here. This is a shift, not quite a shifted version of something that's in my table, because if I'm thinking of, that little f of t is t squared, then big F of s would be 2 over s cubed. I need a 2 here in order for this to look like a shifted version of something that's in my table. So I can manufacture that 2 by putting a 2 here and multiplying by a 1/2 out front, because those undo each other. I already pulled the A out, pulled the B out, pulled the C out. Similarly, I'll pull the D out. This is in my table. So now I'm ready to go. This A remains. This inverse transforms back to e to the t. The B remains. This inverse transforms back to, remember, this is a shift in the S domain, so it's and it's a shift of 1, so it's a multiplication by e to the t. You cover up your shift. This is a 1 over s squared. When you cover it up, that inverse transforms back to a t. We have a 1/2. We pull the c out. When we look at this and we cover up the shift, we have a 2 over s cubed. That inverse transforms back to a t squared, but we can't ignore the shift. The shift is a multiplication by an e to the t, because our shift was 1. Lastly, we have our d. This is in our table, so we straight away invert it. And so this is our y of t, but remember, we know the numbers for A, B, C, and D. You could have put them in up here, that's fine. I just held off and I substitute them in right at the end because these numbers were a little bit messy to write, but this is the solution to our initial value problem. Notice you don't have to find YH and YP separately. You don't have to go through and find the constants that satisfy your initial conditions. Now, you had other work that you had to do. Really, you're sort of going to pay your taxes somewhere. Here we paid our taxes in the partial fraction decomposition and in the inversion process. Whereas in using another method, you're sort of paying your taxes by having to find the YH, the YP, which can be quite involved, and then finding the initial condition, the constants that satisfy the initial conditions. So it's just a nice study in contrast. Let's look at one more example. And let's look at an example of one that you could not have done using the Chapter 4 methodology. So consider the initial value problem, y double prime plus 4y prime plus 13y equals g of t, where g of t is this piecewise defined function. We haven't seen something like this before. So g of t is going to be 0 if t is less than 1, and then it's going to jump to 1 when t is greater than 1. We really don't care what happens at 1. You could make this an or equal to. It doesn't affect anything. Think of this as a switch that's off until time 1, and then exactly at time 1 it kicks on and turns on. These are common types of g of t's that occur in many electrical systems. They can also occur in mechanical systems. And let's just have the initial conditions y of 0 is 0 and y prime of 0 is 0. So just like we always do, we're going to start with our differential equation. We're going to take the Laplace transform of both sides. We'll do the Laplace transform of this in just a minute. Let's concentrate on doing the Laplace transform of this. This is not in our table, so we just have to fall back on the definition. We'll use the integral definition. We did some of this in 7.2. We find the Laplace transform of this using the integral definition. When we do that, after the dust settles here, we get e to the minus s over s. So the Laplace transform of this, you have to be flexible here. Sometimes it's something that's in your table, but you can always go back to the foundational definition if you have to until our table becomes more fully developed. So here our Laplace transform of our g of t comes out to be this function. So let's Laplace transform this. But here we just Laplace transform the pieces. Here we use our second derivative theorem. We get this. We pull the 4 out and use our first derivative theorem. Parentheses are very important here. And then we have plus 13 times our big Y of s. So when we do this, we get this. And when we do this, we get this. So now let's apply our initial conditions. These are all 0. That makes this very nice. And then we just divide by this here. And now stare at this for a second. Normally here we would, up to this point, we would go do a partial fraction decomposition, and then we would be prepared to inverse transform after we did a partial fraction decomposition. But if you stare at this, we can't do a partial fraction decomposition on this because remember, partial fractions requires this to be a polynomial over a polynomial. This is not polynomial. So we're at an impasse right now. So how in the world would we inverse transform this? We cannot use partial fractions due to the fact that this is not a polynomial in the numerator. So nothing in our table helps. And I wanted to finish with this example to show that this is the motivating fact for expanding our list of things that are in our table, because the wider of a list of things that are in our table, especially in the right-hand column of our table, that means the more robust our methods are to inverse transform, because we like to read the table from right to left in order to inverse transform functions, and that's exactly what we need to bring this back to the t-domain. We have to be able to inverse transform this. Unfortunately, that this is just not something we know how to inverse transform yet at this stage, but we will do so in the coming sections, and then we'll finish this problem.